Good morning, Build Stuff. How are you all doing out there? Those of you who are rocking out with us at the party last night, I hope the hangovers are not too serious and you're ready to learn some more awesome and amazing stuff. Those of you who are joining us online from all over the world, I hope you had a good time last night and the hangovers are not too serious and you're also ready to learn some good stuff. Next up on our virtual Jupiter stage, joining us streaming live from Istanbul and talking all about building highly scalable face recognition pipelines. Please give a big, warm Build Stuff welcome to Sefik Serengil. How you doing, Sefik?
Hello, I'm good. How are you?
Very well. The stage is yours, my friend. Take it away. Teach us something cool.
Thank you. Hello, everybody. Thanks for coming. I just want to thank first Build Stuff 2021 conference organizers for inviting me. Also, my employer, Yapı Kredi Technology, for supporting me to come here and talk. Today, I'm going to talk about facial recognition, but we will focus on facial recognition as an end-to-end pipeline. Besides, we will also require highly scalability. Let me introduce myself first. This is Sefik. Currently, I'm a software engineer at Yapı Kredi Technology, which is a subsidiary company of Yapı Kredi Bank, which is one of the largest banks in Turkey. What's more, I'm a contributor of many open source projects. In particular, I'm the creator of deepface and I'm still maintaining it. That's highly adopted by the community, adopted by the open source community actually. And today it has 2,000 plus stars on GitHub and 250,000 plus installations on Python package index, PyP. This is because I'm talking in this conference today. I have a personal blog, sefix.com. I write here technical tutorials, mostly related to programming. Also, I'm creating online content on YouTube. By the way, I appreciate if you subscribe my channel. And finally, you can find me on Twitter with my surname as Serengil. If you mention me about anything during this talk, I promise I'm going to answer. And let's start. We are going to talk about facial recognition, and there are actually 5 common stages of a modern face recognition pipeline. Those are detection, alignment, normalization, representation, and verification. We are going to visit those stations one by one in this talk, and let's start with the first stage, which is face detection. Actually, I'm going to talk about facial recognition with deepface framework, and deepface wraps many cutting-edge face detectors. Those are OpenCV, SSD, MTCNN, DLIP, and retina face. If your task requires high confidence, I recommend you to use retina face or MTCNN because those detectors come with high scores, but they are actually slow. On the other hand, if your task requires high speed, then you should consider to use OpenCV or SSD. Those are very fast detectors, but their detection performance is a little bit less than the MTCNN and retina face. We are going to mention that we will feed pre-processed images to deep neural networks in the following stations. And the neural networks models expects standard input size. So resizing is required, and when you detect the face, you have to resize your image. For instance, if you resize a rectangle image to a square one, then it's going to be deformed. That's why here deepface is adding padding black pixels to avoid deformation. And those are the results of different face detectors wrapped in deepface. You can use any of them with a single argument. We are going to mention it. And as I mentioned, retinal face is the most powerful one. And you are seeing the result of retinal face model in this illustration. It's a deep learning based model, and its robustness comes from here. On the other hand, other detectors such as OpenCV are not modern, are not based on modern architectures, but they are fast, as I mentioned. The detection performance of retina face is amazing, even in the crowd. It can find even the ones in the back rows as seen. The detector also finds some facial landmarks such as eyes, nose, and mouth as seen. Those are highlighted with red points. We can use those landmarks in the next stations of the pipeline. I'm going to mention it. The second station is alignment, and let's visit that station. Here, experiments show that just alignment increases the face detection accuracy more than 100. This score might not seem to offer major contribution, but we already have models with human level accuracy. So we can just make a difference with those little touches. We need the eye positions to align a feature. Detectors wrapped in the deepface can find facial landmarks as well, and we will rotate the image until the both eye coordinates becomes horizontal. The next station is normalization. That's not a must, but we should apply this normalization stage. Face detectors detect faces in a rectangle area, and it might throw some noise information. We can also find the 68 landmarks of a face, 68 facial landmarks as seen on the middle. In that way, we can get rid of any noisy information in a facial image. This stage is called normalization. As I mentioned, that's not the must, but it increased your model accuracy dramatically. The next station is representation. And it's very important because we are going to use deep neural networks here. But the usage is a little bit different than the regular neural networks. That's why we are going to spend a lot of time in the station. Neural networks, and especially convolutional ones, dominate computer vision studies recently because convolutional neural networks are very good at detecting some patterns in visual data. So facial recognition models are mainly based on convolutional neural networks. And suppose that you have a data set consisting of 100 identities, and each identity might have multiple facial photos as seen in this page. We are going to build a CNN model, and its output layer should have 100 nodes because our facial database has 100 identities. That's the same number. When we feed the images of, for example, Angelina Jolie, its corresponding output should be 1 and others should be 0. That's the expected target. And we are going to train the neural network with this input and output pair. And neural networks will tune its weights based on this input and output pair. Similarly, when we fit the images of Jennifer Aniston, we set the corresponding output to 1 and others to 0. Then neural networks continue to tune its weights. We are going to apply this approach for each identity. In that way, we define the facial recognition as a regular classification task, and there are 100 identities in the output. We already know that CNNs are very good at classification, and we can guess this approach is going to work well. But what if a new person would join into our database? That becomes very problematic. As a first approach, we can add a new node corresponding to, for example, Katy Perry in this illustration into the output layer, and it's going to be 101 output nodes. This is not going to work because our model structure is changed. Firstly, our model will become more complex when a new member joins. We need to retrain the model always when a new member comes into our database, and we won't have a centralized model. Each company, each institution should train its own facial recognition model. The question is that what if the new model underperforms? We really need something different here. As an alternative approach, we won't add a new node to output layer. It will remain same. It's going to be 100 output nodes, and there is no corresponding node for the new member, Katy Perry here. And once you fit the facial image of Katy Perry, the network will produce an output for her anyway, as seen in the right. And we will call this output probabilities as vector embeddings. And we will use those embeddings in facial recognition tasks. So in that way, we have a generalized model. We don't need to retrain the model anymore when a new member comes. We will train it once and use it always. And model complexity is always same. Here, there are lots of state-of-the-art facial recognition models in the research area, in the market, and deepface has been expanding its model portfolio since its first commit. Its initial version just wraps VGG face model and FaceNet model, Google FaceNet model. Now it supports 7 different cutting-edge face recognition models. Those are actually deep neural networks models with different structures. Notice that those models are already reached and passed the human level accuracy. But also in the future, we will able to easily use the latest facial recognition models into our portfolio. And the final stage is verification. Let's visit that station. But before that, we are going to talk about the distance. And I want to read a poem of a famous Turkish poet here, Can Yücel. We have been talking about very different, very confusing concepts. This might help us to recharge our batteries. The name of the poem is The Longest Distance, because we are going to talk about the distance. And the poem is the longest distance is not to Africa or China or India, not to the planets or the stars that sparkle in the night. The longest distance is between two minds that don't understand each other. And luckily, we do understand each other. And let's make the concept of distance. We are familiar with this illustration with social distancing, but we are going to just talk about the distance. We represent facial images as vectors in the representation station. And we expect that here vector embeddings of same person should be more similar than the embeddings of different persons. We can formulate the similarity of a pair with the height school method actually. And please remember the Euclidean distance formula. This is not the only way, but it's very easy to remember. We need to find the sum of the squared difference of dimensions to calculate the squared distance. This is an example for three-dimensional space, but face recognition models actually produces vector embeddings with hundreds or thousands of dimensions, but this formula is still applicable for multi-dimensional vectors. So we have the distance values between vectors and corresponding facial images. How to determine they are same person or they are different persons. This graph shows the distance distribution for both same person and different persons in a large database. The distance values for same person seem to be less than the distance values for different persons. Here we can determine a threshold value based on this distribution graph, for example, 4.5. And we will verify pairs if the distance value is less than that threshold value. I mean that if the distance value between two vectors is less than the 4.5, then that's going to be same person. Otherwise, that's going to be different persons. Here you see the distance values between image pairs of Emilia Clarke and Lina Headey. If we set the threshold to 4.16 here, then we can verify all instances correctly. Even though, for example, daily appearance of Emilia Clarke and her role in Game of Thrones don't look like each other, our model can verify them because as distance is 4.02. We have mentioned all required stations of a modern face recognition pipeline until now. We unboxed the deepface in that way, but luckily you don't have to do any of those stages manually because deepface handles all of those stations in the background, and you don't even need to acquire in-depth knowledge about the processes behind it. And you are able to run facial recognition with a few lines of code in that way. Firstly, deepface is a Python package, and it's fully open sourced and licensed under MIT license. In other words, you are completely free to use it for both personal and commercial purposes. It's published on Python package index with release history. And that's the repo address. You are able to access it. You just call the verification function of deepface in its interface and pass the exact paths of image pairs as shown in this code snippet. We are going to verify image1.jpg and image2.jpg. They are same person or they are different persons. We just need to install the package with pip install deepface command. Once you installed the package, then you are able to import the library with from deepface import deepface command. Then you are able to call its functionalities. For example, verify function in this example. Then it's going to return the decision image1.jpg and image2.jpg. They are same person or they are different persons. The result is seen in the verified key in the result, and it seems that they are same person. And there are some additional fields such as the distance value and the threshold value we determine to verify. For example, here the distance value is 0.32 and it's less than the threshold value 0.4. That's why it's going to be verified. And remember that we just fit the exact image paths to the deepface library. As mentioned, deepface wraps many state-of-the-art face recognition models and face detectors. And you can switch among its face recognition models and face detectors portfolio with an argument. All functions and its interface accept optional model name and detector backend arguments. And you can switch among face recognition models and face detectors here. The default face recognition model is VGG face, and the default face detector is OpenCV, but you are able to use Google FaceNet, OpenFace, Facebook deepface, deepID, dlib, or ArcFace as the face recognition model, or OpenCV, SSD, dlib, MTCNN, or retina face as face detector. We mentioned face verification, and we fit image pair, and we determine they are same person or they are different persons. This is face verification actually, and its time complexity is O1 because we have the image pair and we just determine. Face recognition studies mention this task. Actually, face recognition studies mentions face verification, but face recognition is a little bit different in daily life. If you want to look for an identity in a database, that's going to be face recognition actually, and it requires to run face verification many times. That's why its time complexity is going to be ON in the big O notation, where N is the number of instances in your database. ON would be problematic when N becomes really big, millions or billions. As mentioned, face recognition requires to run face verification many times, but you don't have to do it manually, and deepface has a dedicated face recognition function. You should mention the identity you are looking for in the image path argument here, which is target.jpg. And I also mentioned the database path. Here, users /Sefik /db is a folder, and there are many face photos in this folder. Then deepface is going to find the target JPEG in that database path. This is the result of the find function. It's going to return the identities it found. And it also returns the distance values and determined values as well. In addition to face verification and face recognition, deepface has a facial attribute analyze module as well. And we can analyze age, gender, race, and emotion analyze with this functionality. It basically analyzes apparent age, and it returns the number in the age cache in the result. It also returns the probabilities for 6 different emotion and also 6 different race, but it also returns the dominant emotion and dominant race and gender also. With this analyze function, we intend to decrease the search space with demography in facial recognition. We also plan to fight with biased data sets in the training of facial recognition models. Here, age prediction model has plus and plus minus 4 years error score, whereas gender prediction model has 97% accuracy, and its precision and recall values are almost same, 97%. And as mentioned, we just fit the image exact image path, and find function returns age, gender, emotion, and race ethnicity. And let's consider the problem as a large scale problem and highly scalable perspective. Here I'm going to ask a question to the audience, but they cannot answer for me. I wonder, anyone wonders how Google run reverse image search algorithm. Here we know that we fit the image of Angelina Jolie in the left side, and it returns the similar ones in the milliseconds. We guess that they are using a convolutional neural networks model to convert images to embeddings, vector embeddings. Then it will return similar images with close embeddings. We guess that. However, Google indexed already 100 billions of images. And how can Google perform a query in milliseconds? Is it related to the hardware they have? The second question I'm going to ask the Facebook way. Facebook image tag model applies same procedures when an image edit, even if the other is not your connection, its face recognition model can find you in seconds. Here, Facebook has billions of users and probably 100 billions of images in its database. But how can Facebook perform that query in seconds? Is that related to the hardware Facebook has? Here, a well-known Turkish photographer mentioned that if the best camera had taken the best photograph, then the one would be the best novelist who has the best typewriter in the all time. Similarly, query performing times in both Google and Facebook should not be related to the hardware they have. We can actually group the items in our database with demographic information, and I mean that deepface can already find age, gender, and ethnicity of an image. We can store the information for those items in our database. Then you can decrease your search space when you are going to search an identity, because you will be able to know the demographic information of the one you are currently looking for. However, you are still needing to run a search problem on a large space. Here, Google and Facebook are running approximate nearest neighbor algorithm instead of KNN algorithm, K nearest neighbor algorithm. That's why the time complexity becomes really small when it's compared to the value of n. Actually, Spotify is using that algorithm to recommend playlists. Currently, we have some open source packages to run this algorithm, approximate nearest neighbor. Those are Spotify Envoy. It's the acronym of approximate nearest neighbor. Oh yeah. Secondly, Facebook Face. That's the acronym of Facebook AI Search Similarity Search. Sorry. Thirdly, NMSLib. That package is developed by the 4 PhD students, and it's the acronym of non-metric space library. And Elasticsearch actually wraps NMSLib, but it comes with highly scalability. Also, Milvus and Pinecone are vector databases nowadays we have. Those frameworks are open sourced to run approximate nearest neighbor algorithm. And this algorithm has a very small time complexity, but it applies a heuristic approach. That's why you might miss some close vectors as seen here. You can use deepface to extract facial embeddings as well. You pass the exact image path, then it's going to return a multidimensional vector. You can store the output vectors as is in the technologies we are going to mention to run approximate nearest neighbor or KNN algorithm. For instance, you fit the image of Angelina Jolie here to deepface, then it's going to return a vector with 622 dimensions. It's the output size of the VGG face model wrapped in deepface. You can think output as an multidimensional array in the regular programming languages. Array with 2622 items. We are going to discuss here the recommended tech stack for face verification and face recognition. If you are going to run face verification, then the time complexity of your task is O1, as mentioned before. Please consider this use case for face verification. We will log into a mobile application of a bank, and bank should store facial embeddings of its all customers in a data store. You can firstly store the vector embeddings in regular relational databases. However, vectors or arrays are not valid data types for relational databases. That's why you should store each dimension value in a column or row here. Here, Oracle, DB2, or SQLite are common technologies for relational databases, and you can adopt those tools easily. But as a better way, you can store your embeddings in a key-value stores, such as Redis or Cassandra. Relational databases are good at store and collect relational data, but in our task, we need just an embedding of a customer. In that case, relational databases cannot work as fast as key-value stores because they cannot reach the O1 time complexity in the best case. Besides, but key-value stores perform O1 averagely. Besides, you can store vector values in key-value stores as is. I mean that arrays are valid data types in key-value stores, and the technologies I'm going to mention in the slide. I mean that you don't have to expose the dimensions and store each value as a value in the database. Notice that face verification is a subset of face recognition. So you can use the same tech stack of face verification in face recognition tasks as well. But when data size becomes really big, you might consider that millions or billions level, those tools are not going to work. Here, you can apply K nearest neighbor algorithm or approximate nearest neighbor algorithm. It depends on the priority of your task. If your task requires high confidence, for example, you are going to search a guilty in a citizen database, you should use KNN algorithm because it guarantees to find the closest one always. NoSQL technologies such as Hadoop, Hive, Spark are good at running KNN in this case, but you have to have a very powerful hardware to run this algorithm on a large-scale dataset. On the other hand, if your task requires high speed instead of the confidence, you should use ANN algorithm here. Here, reverse image search of Google or Facebook facial image tag module are examples for that. We have those tech stack for running ANN algorithm: Spotify Annoy, Facebook Face, NMSLib, Elasticsearch, Pinecone, and Milvus nowadays. We are coming to the end of the presentation, and I'm going to conclude the speech. To sum up, deepface is a lightweight face recognition framework. You can use any functionality, including face verification, face recognition, face analysis, and face representation with a single line of code, as mentioned in the code snippets in my talk. You don't even need to acquire in-depth knowledge about the processes behind it. Secondly, it's very easy to install and run. Some of the popular facial recognition libraries require core C and C++ dependencies. That makes them very hard to install and initialize. You might have some troubles in the compile stages. However, deepface is mainly based on TensorFlow framework, and that makes it very easy to install and run as well. Thirdly, deepface currently wraps 7 different state-of-the-art face recognition models and 5 different cutting-edge face detectors. The list of supported models and detectors has been expanding since its first commit, and we will continue to grow over the future. Fourthly, deepface is licensed under MIT license. This means that you are completely free to use it for personal and commercial purposes. Besides, it's fully open sourced, and all pull requests are welcome. You can customize the library based on your requirements as well. Moreover, the deepface has a growing community. It's highly adopted by the open source community, as I mentioned. Currently, there are tens of contributors, thousands of stars, and hundreds of thousands of installations. Even if you face an issue, you will likely find the solution in the discussion forums, such as Stack Overflow. And finally, deepface is a language independent package. Even though its main functionalities are written in Python, it serves as an API as well. In that way, you can run facial recognition and facial attribute analysis from your mobile application or web application as well. So a review of modern face recognition pipeline has been done in my talk, and then the description of the developed lightweight deepface framework has been made. Deepface makes facial recognition very easy and simple. We aimed at. We then mentioned how to use deepface with some accelerating technologies to make it highly scalable. I thank you all for watching. If you have any questions, I will be happy to answer. And that's the end of my talk.
Great stuff. Thank you very much, Sefik. That was really, really interesting stuff. Nice combination of theory, real world examples, and a lot of good stuff at the end there that I always think the mark of a good talk is when it gets to the end, I'm like, I want to go away and play with that and see how it works. And I certainly got some links out of that one. Folks, any questions for Sefik, please drop them in the chat now. We have a couple of minutes. We will drop in the Zoom Q&A link. There is going to be a live question and answer session running on a separate Zoom. So Sefik, I'm going to drop a copy of that here in our little Zoom chat so you can follow up on that. Q&A link is here. For all the folks who are watching us on the stream. No questions in chat yet, so I'd swing over to that Zoom. If you have any questions, you can meet Sefik in there and chat about facial recognition pipelines and all the stuff that he showed us. Thank you so much, Sefik, for taking the time to join and share your insight with us today. Thank you very much to all the folks who are watching us online. Thanks to the folks watching us in person in Vilnius. Good to see you.